Hello, this is Miss Spivey. We are still working in Unit 4 on bonding. This is video lecture number 2. So if you have not already watched the lecture on how to draw Lewis structures and why we draw Lewis structures, please go back and watch that video because I'm going to assume that you understand what I'm talking about in this video. So things that we're focusing on in video number 2 for Lewis structures in chapter 4, we're going to draw double and triple bonds in molecules. We are going to have expanded octets, so when our center atom can hold more than 8, and also exceptions to the octet rule. Okay, so things that you need in order to be successful with this unit or this video, you need your Unit 4 book. You need the piece of paper that you were drawing examples on yesterday. You might need a calculator. You definitely need a periodic table. I would make sure that whatever you're writing with is a pencil, not an ink pen, because we're going to need to be doing some erasing today. Okay. All right. So let's get started. So what I want you to do first, I want you to open up your unit book to page number 4. Page number 4 of your Unit 4 book. I'm going to be looking in the middle of the page. Okay, so types of covalent bonds. In lecture 1, we drew nothing but single bonds, okay, where we have 2 atoms with only 1 bond in between them. But you can have double bonds and triple bonds as well. So remember, anytime you have a bond, like you see on the screen, those are 2 electrons. So if you have a double bond, that means that I have 2 electrons in one bond, 2 electrons in another, 4 electrons total. Okay, so remember, our magic number of total electrons is 8 electrons or 4 pairs. Okay. So I'm looking at the bottom bullet of that section. It says multiple bonds are commonly formed by carbon, nitrogen, oxygen, phosphorus, and sulfur. The acronym CNOPS will help you remember the symbols of those elements that can form multiple bonds with themselves and with each other. Highlight that. The only atoms that are going to have double or triple bonds are CNOPS. Okay? You can't have double and triple bonds all the time. We don't even need them all the time. But the only atoms that are able to form double and triple bonds are CNOPS. Okay? The next bullet. Multiple bonds are stronger than single bonds, so therefore it takes more energy to break a double bond than a single bond, and still more energy to break a triple bond. The last bullet says multiple bonds increase in electron density. As the electron density increases, the repulsion between the 2 nuclei decreases. Also, electron density increases. The attraction each nucleus has for additional bonding electron pairs increases. Both of these effects draw the nuclei closer together, shortening the bond length. So that means the distance between the 2 nuclei is shortest for a triple bond. So when we're drawing our structures, all of our bonds are probably going to look the same, right? Like if you look at my pictures here, this double bond looks the same length as this triple bond. But in real life, what's happening at the atomic level is the triple bond is the strongest and it's also the shortest. The atoms are just closer together, okay? So we are really going to apply our multiple bonds. If you look at our rules for drawing Lewis structures, I'm there on the bottom of page 4, we're going to follow all of the steps that we did yesterday. Flip over to page 5, except today we have to focus on number 8. If the central atom is not yet surrounded by 4 electron pairs, convert 1 or more terminal atom lone pairs into double or triple bonds. Remember, not all elements form multiple bonds, only CNOPS. Okay, CNOPS is it. So what happens a lot of the time after we teach this section, I'll start looking at pictures and you guys want to put double and triple bonds everywhere all the time. What you have to remind yourself is the center atom is happy or stable with 4 pairs, 4 electron pairs, whether they are shared pairs like a bond or lone pairs, okay? So after your center atom has 4 bonds, stop, okay? So let's draw an example. Let's go to your paper. Let's draw carbonate, CO3 with a -2 charge. Still following the same steps as yesterday, okay? So 4 valence electrons from carbon plus oxygens in group 6. 6 times 3 is 18 plus 2, so that gives me 24 total. Okay, step number 2, divide by 2. That gives us 12 pairs left. Okay, I pick the atom with the lowest electronegativity, step 3, to go in the center. So I draw my oxygens on the outside. All right, now I draw 3 bonds, 1, 2, 3. I subtract. 12 minus 3 gives me 9 pairs left. Now, just like Rule 7 says, place lone pairs around the terminal atoms except for H to satisfy the octet rule. So everybody wants 8 total electrons or 4 pairs. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have used up all 9 of my pairs. So I cannot draw more pairs. I can't just add them on. I have to do a little bit of thinking. So when I look at my oxygens, everybody has 4 pairs. They're all happy, but the carbon, the center atom carbon, only has 3 pairs. So this is where I'm going to need to make a double bond. What we're going to do is we're going to erase a lone pair. There's the bell to go to lunch. Sorry about that. I erase a lone pair and I make one shared pair. So you can see now I have a double bond and 2 single bonds between my carbons and my oxygens. I don't have to keep bonding because if you look at your center atom now, it has 1, 2, 3, 4 pairs, and that means it's happy. Now you might be saying, oh, but how did you know to put the double bond there? It could go over between the other oxygen or even the other one. Very good. That means that this structure has resonance. Resonance is a vocabulary word you need to write down. That means that there are multiple correct structures because the double bond or triple bond can correctly be in multiple places. Okay, so another correct way to draw carbonate would be like this. Or even this. Okay, resonance structures, multiple correct structures because the double or triple bond can be in several locations. Okay, all right, let's try another. All right, next, let's draw CS2. Okay, still following our same rules. Carbon brings 4 valence plus sulfur's in group 6. 6 times 2 is 12. 4 plus 12 is 16 total. All right, 16 divided by 2 gives us 8 pairs in our picture. I put carbon in the center because it has the lowest electronegativity. Put sulfurs on the outside. I need 2 of those pairs to be as shared pairs, 2 covalent bonds. So that means I have 6 pairs left. Anytime I have extra, I start at the outside first. Okay, so I'm going to use dashes for my lone pairs this time. So here's 1, 2, 3, 4, 5, 6. I've used up all 6 pairs of my electrons that could be in my picture. Okay, so my sulfurs look good. They have 4 pairs. They've satisfied the octet rule. But when I look at my carbon, let's see if I can put an arrow to it. When I look at my carbon, it only has 2 pairs, okay? So what we need to do is I'm going to erase one lone pair between my sulfur, on my sulfur, make it a shared pair, put it in a different color just so you can see it for dramatic effect. Even after I've made that one double bond, my carbon is still not stable. So I'm going to need to bond again. Okay, so I erase. Sorry, my eraser kind of didn't work. And I make another double bond. Okay, now carbon has 4 pairs. The sulfurs all have 4 pairs. We're finished. Okay, that's it. This structure also has resonance because you could make a triple bond and a single bond, and so then therefore the triple bond could be in a couple of different locations. Okay, so I have multiple correct structures because my bonds can go in several places. So one more example on double triple bonds. If you'll go to page 7, and let's look at number 2 on page 7. Number 2 on page 7. Number 2, page 7. And that is CO, carbon monoxide. So we still follow the same steps. 4 electrons from carbon, 6 from oxygen gives us 10 total. Divide by 2 gives me 5 pairs. Now, step 3 says to put somebody in the middle, the lowest electronegativity. Well, I only have 2 different atoms, so technically I don't have a middle. That's okay. I can still have my 2 atoms near one another. I bond them with a covalent bond, and I have 4 pairs left. So my rules say to start filling up on the outside. Well, pick one. So I'm going to put 1, 2, 3 pairs around oxygen, 1 pair around carbon. So I've used up all of my electron pairs, okay? Now, the oxygen is good. It has 4 pairs to it, but the carbon is not. So I'm going to erase a lone pair, make it a shared pair. Carbon still isn't stable. It still needs 1 more pair. So I erase and share. And there we go. So here is the correct structure for carbon monoxide. So again, follow all the same steps as before, but pay attention to number 8. If your center atom isn't happy, center atom needs 4 pairs. But you can only double or triple bond if your center atom and the atoms that it's bonded to are in synops. Okay? So like if I look back at our structure for carbonate, let's say that one of these oxygens was a fluorine. Okay? Fluorine is not part of synops, so it can't double bond. Okay? Only the atoms in synops are allowed to double and triple bond. So I'll give you a couple of extra pages to practice in just 1 second. I also want to look at what's called expanded octets and exceptions. Okay, so let's look in your unit book. If you feel overwhelmed, you need a little break, pause the video, and then come back. Okay, so I am at the bottom, not the bottom. I want you to go to page number 5 in your unit book. And I'm going to look in the heading, it's in bold, it says exceptions to the octet rule. So a few elements will have fewer than 8 electrons. Hydrogen only has 2 electrons. Beryllium has a maximum of 4 electrons. Boron is stable with 6 valence electrons. I want you to add aluminum to that list as well. Boron and aluminum are stable with 6 valence electrons. So let's think about that in terms of our electron pairs. So exceptions. So that means that the center does not need 4 pairs. Okay, so number 1, hydrogen can never go in the center. Okay, it is happy with 1 electron pair. Okay, beryllium, if it's in the center, it's happy with 2 electron pairs. boron, and aluminum are happy with 3 electron pairs. Okay, so that means if they're in the center, they do not need 4 pairs, they're happy. Okay, but just remember, hydrogen never in the center. I really strongly emphasized that yesterday. Hydrogen's never in the center and it never has lone pairs. Okay, now let's look at what's called an expanded octet. The bottom paragraph on page 5. Also mentioned above, elements in periods 3 through 7 are often able to expand their octet and may have 5 or 6 electron pairs around the central atom. This is due to the availability of d orbitals that begins with the 3rd energy level. Even if the original atom has no electrons occupying d orbitals before bonding, these empty d orbitals can be drawn into the hybridization process. So an expanded octet is what's going to happen when your center atom has more than 4 pairs. Okay, so again, that's only for center atoms in period 3 through 7 because there are d orbitals available. Okay, so we're not always going to have expanded octets. We're not always going to have exceptions. We're not even always going to have double and triple bonds. Okay, this is where the problem solving aspect of Lewis structures comes from. So if you follow your steps on page 4 and 5, that procedure that's written, and you are really sure to be verifying your octet rule, you will never draw a structure the wrong way. So let's draw just a couple more examples. Let's do BR F5. All right, bromine is in group 7. 7 plus fluorine's also in group 7, so 7 times 5 is 35. That gives me 42 total. That's the largest amount of electrons that we've had so far. Okay, this is going to be a big molecule. So divided by 2, that gives me 21 electron pairs. I picked the atom with the lowest electronegativity in the center, so that's going to be bromine. Now I need to position 5 fluorines around the outside. So just do so to where you have plenty of room. Remember, electrons are negative. They like to repel each other. So you got to give them their own space. So here's 1, 2, 3, 4, 5. I went ahead and bonded mine. Sorry, I combined step 3 and 4. But we're not going to skip step 6, subtracting the pairs. So I had 21 pairs. I used 6 shared pairs, and so that gives me 15 left. Okay, now I start filling in on the outside. So I pick a fluorine and fill it up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh, I think I did something wrong. Sorry, y'all. I made a mistake up here. I didn't have 6 bonds. I had 5. So 21 minus 5 is 16 pairs left. I apologize. I make mistakes. We all make mistakes. So I have 16 pairs. I just used up 15 around all my fluorines. So that means I have 1 pair left. Just like Rule 7 says, after you fill up the outside atoms, if you have extra, they go on the central atom. So I'm just going to find an empty spot on bromine, and I'm going to put my lone pair there. So there we go. Here is the correct structure for BRF5. Very large. Bromine is in period 4, so it's able to have more than 4 bonds to it. It doesn't have to, but it can if necessary, and it was necessary here. All right, let's do another one. Let's do I3 with a -1 charge. Iodine is in group 7. 7 times 3 is 21. Plus 1 gives me 22 total electrons. 22 divided by 2 is 11. Okay, I have 3 iodines. So you know what I'm going to do? Put 3 iodines in a row. One of them's technically my central atom. I draw 2 covalent bonds, so 11 minus 2 is going to give me 9 pairs. And I start filling in my outside iodines first. So I'm going to use dots in this picture, trying to help. I know we all use different things. So there's 1, 2, 3, 4, 5, 6. I still have 3 pairs left. And they have to go on the center. But I'm going to position them far away from each other. So here's 1, 2, 3. So I finally used up all of my pairs. Again, iodine is in period 5, so it can have more than 4 bonds if it needs to, because it's in periods 3 through 5 and it has d orbitals. One more example. Let's draw AlH3. Aluminum is in group 3. Hydrogen's in group 1, but I have 3 hydrogen atoms, so that means it has 3 electrons. That gives me 6 total. So this one's small in comparison to what we've been doing. 6 divided by 2 is 3 pairs. Okay. Aluminum in the center. I draw hydrogens on the outside. Okay. I'm going to draw 3 bonds, 3 covalent bonds. And so I'm left with no pairs. And you're like, oh, but my hydrogens don't have dots. Remember, hydrogen will never have lone pairs, ever. It's satisfied with only 1 total electron pair. And then when you look at your center atom, you might panic and you might say, oh, aluminum's not happy, but I don't have any lone pairs that I can erase and share again. Well, aluminum is an exception to the octet rule. It doesn't have to have 4 pairs. It can, but it doesn't have to. Okay? Plus, aluminum is not in CNOPs. Okay? The only time you can have a double or triple bond is if your atoms are carbon, nitrogen, oxygen, phosphorus, or sulfur. Okay? So I hope that you are feeling confident about your Lewis structures. Okay? You're really following the same procedure over and over and over again. But today we did add a little bit of problem solving in the sense that you need to make sure that you look at your center atom. Center atom have 4 pairs. Okay? If yes, then you're done. Yay! Okay? If no, okay, is it part of CNOPs? Is it an exception? Okay? If it's part of CNOPs, then you're going to make a double bond or a triple bond if you need it, but make sure that you stop with 4 pairs on your center atom. If it's an exception, then that means you've got boron, beryllium, and aluminum, and you'll be good to go. Hydrogen's never in the center. And then remember that we can also have expanded octets in period 3 through 7. So we can have more than 4 pairs. So if you need extra practice with Lewis structures, here are the pages that you need to go and work now. Okay, page 7. You can finish it. I drew 1 picture on page 7. Okay. You can also do page 8 and 9. Page 8 and 9 have divisions between them and boxes where you can draw your Lewis structures. But just remember, we are following the same steps over and over and over again. So, hope that this lecture has been beneficial for you. And again, if you need our help or you need to work with an actual teacher and not just listen to a lecture, communicate with your chemistry teacher. We are happy to help. Thank you for watching and enjoy the rest of Unit 4.